How you guys doing today? Good, perfect. I know you guys super busy with lots of finals, but you guys know that, right? Our final exam will be on campus online. Make sure you check the date and time, and just do it. It's open book test. Not much stress on the memorizing, but normally, historically speaking, final exam is easier because it's open book test. Alright, today I'm going to finish up hopefully I can finish up the chapter 11. And then I'll probably start holding a review on Friday and Monday twice, but solely on chapter 10 and 11. So you can start watching the exam 1 and 2 review sessions, but still you can save a lot of time by just. Okay, we've been talking about SN2 reaction. Okay, so I don't know if you have been watching the video on the YouTube. This means the substitution. Okay, and the N stands for this nucleophilic. So you have some nuclear file to cause the substitution reactions, and 2 means it's a bimolecular. So meaning, whenever you have leaving groups, okay, the nucleophile coming into the back, not on the front, because this one has to leave, and also this will actually show you transition state. Transition state, okay? So if they form something like this, okay, so this is about to be formed on the back. This is about to be broken soon with the leaving groups. That is why whenever you do SN2 reaction, your addition of the nucleophile will be always going to be the back of where you have the leaving groups. Okay, so this is what we're talking about. Okay, this is what we're talking about, and this is bimolecular, so it depends on your leaving groups and your nucleophile concentration. Because you have 2 factors will control the speed of the reaction. So this one, because it shows the transition here, and this is why you're going to see the inversion of stereochemistry, because you're gonna have leaving groups leaving on the other side, but you have a new nucleophile coming into the back. So we'll change the stereochemistry. Okay, so this is what we'll be talking about. And then that is the reason why if you have a more bulkier on the carbon with the leaving groups, it will be slower in SN2, because if it's more bulkier on the carbon with R groups, it's the leaving groups. The nucleophile will be harder to approach from the back because there's so much bulky R groups on this carbon. So if it's less substitute or less symmetric carbon on the leaving group, should be the easiest one for the strong nucleophile to tack on the back, because it's just hydrogen. Okay. Guys, remember this or some? Okay. So this is what we're talking about. So we have the leaving groups, but sometimes, like I showed you last time, the trend of the leaving groups, better, poor, and so on. Sometimes you have like a poor leaving groups. If you guys remember this on chapter 10, we did it 2 things. You can either do diol chloride. You can also do phosphorus tribromide treatment. So what it does is that they actually form a better leaving groups. So they actually form the better leaving groups, and then later there are strong nucleophile, relatively speaking, coming onto the back. So even though this is a hydrox group, which is your alkyl compound, but this hydrox group is very poor leaving group. So they're not really wants to leave from the compound. That makes the substitution reaction very slow, or not going forward in forward direction. But if you trade with those two, maybe you can have a even better leaving groups, substituting your hydroxyl poor leaving group to the better ones, and then you have a strong nucleophile coming from those two. Once they bond to the hydroxyl group, or attack on the back, so they can have substituting the hydroxyl group on the back side of radial glass. Okay. This will be. Is it working well? Can you guys see this actually? Is it okay? Oh, yeah, okay. Let's try to try. Oh, let me try this one. Yeah, just there. Okay. But does it make sense? Okay. So this is the poor leaving group. In those cases, this is what we did on chapter 10. This is why we did this one. Because the hydroxyl group will not leave the compound easily. That's why we're going to switch this one to these two. And then they can have better leaving groups. And later, strong nucleophile can attack on the back. So we're switching this one, but we'll be switched on here. Okay. So that's the SN2. Does it make sense? Okay. Okay. All right. So the this is very important. Solvent. Okay, solvent. So what solvent you need to do the SN2 reactions? We're gonna use some polar aprotic solvent. So polar aprotic solvent simply means it's polar compounds. Solvent molecules are polar, but they're not able to form. They're not forming hydrogen bond. Okay, so that means those polar compounds do not have a hydroxy group or amine groups to do some interact with the compounds in the hydrogen bond formation. We'll still have a polar compounds, but not able to do a hydrogen bond is the best one for SN2. The reason why is whenever we are very strong nucleophile, okay, so once again, the SN2 reaction will be better if you have a strong nucleophile. Means you have the nucleophile with a negative charge, which means you'll be stronger than what? Neutral nucleophile, because it's more electron richer in the negative charged nucleophile. Obviously, it's more electrons. So it is better if you have a stronger nucleophile for SN2, because they will have a much stronger reaction, because it's more electron rich. We'll find more electron poor carbons, and we'll proceed in the reactions. But that means it's a negative charge most of the time. And then if you have, next, for example, this is a hydroxyl groups on the R with your solvent. Okay. Sort of thing. So this type of thing may do form like a hydrogen bond cage. Because this is a negative charge. So this OH group, this hydrogen is partially plus charge, partially negative charge on the hydroxy group. So thus the polarity here with the strong hydrogen bond able compounds can kind of cage this negative charge nucleophile. So what happens to this one is the nucleophile will be stabilized. Because it's a negative charge means it's unstable, right? Because it has a charge, okay? But it's surrounded by certain partially positive, like hydrogen in the hydroxy group, and caging it, and that makes this nucleophile a bit less reactive. It means it's more stable. So more stable means what? Less reactive. Same meaning, right? Then your SN2 reaction will be slowed down. Okay. So if you want to do really good SN2 reactions, you have to use the still polar compounds, but something that do not have either hydroxy group or amine group. They will not cage your strong nucleophile, which is with a negative charge, so you can have a faster rate of the chemical reactions, SN2 reactions. Does it kind of make sense? Oh, okay. Good. So this is kind of trend. So obviously this methanol is very poor on SN2. So this is this one. As water, that's a good choice. But you can add a DMSO, which means dimethyl sulfoxide. DMF means the dimethyl formamide. Okay? I'm not going to draw the structure because those ones will actually cover in Orga 2. So formamide means it has the carbonyl group, the hydrogen, with the nitrogen amine group attached to it. Okay, but dimethyl that means it's 3. But this one you're gonna do it on over 2 anyway, so I'm not gonna do it much anyway. But I just want you to remember those compounds are not able to do some. So I'm gonna it's acetonitril, and the best one is HMPA, means it's hexamethyl phosphoramide, meaning you have this one. Okay, so there's no hydrogen on it, so it's still polar, but that there's not able to do some hydrogen bond here. So those ones are polar, but not able to do hydrogen bond. So I just want to remember if you look at those compounds, are polar aprotic compounds, it will be good for SN2. And this is quite important, I think, because later I'm going to tell you again, you might have to distinguish certain reaction from either SN2 or SN1. We're going to do SN1 soon. Normally, the easiest way to find out for you is a solvent. So this is SN2 still, but when we're done with the SN1, like a few minutes later, I'm going to do the solvent too. SN1 and E1, we're going to do maybe today or Friday. Always use the polar protic solvent, which is water or ethanol or mixture. So if you look at any reaction with the like water, ethanol-based solvent, I'll show you in the exam too. Then that is most likely SN1, E1. If it's a polar aprotic solvent like DMSO, DMF, or HMPA, and more it's gotta be SN2 or E2. Okay? It's very easy, right? That's the easiest way to find out, because sometimes it's really tricky to find out if it's going to be SN2 and SN1. And I'm gonna show you soon. SN1 shows the different products. So you need to know what solvent is used there to confirm that if the reaction is going to be SN2, SN1. Okay? So just keep that in your mind. I'll tell you more later on today and Friday. Okay? Sounds good? Okay? So solvent is the most key element. You may want to focus on the chapter 11. Okay? So you see this is polar, but there's no hydrogen on it. There's no amine or hydroxy group. I'm pretty sure it's got to be SN2 or maybe E2, but not SN1. Okay, so let's talk about what's SN1 then, okay? SN1. Okay, what about the SN1? So it's pretty much the same. So this is also substitution. Okay, and this is also nucleophilic, that's what it means. And then this one is unimolecular. So uni means, as you know, it's 1. Okay. So unimolecular means it depends on only one factor to control the speed of the reactions. So previously, SN2, you had the compound with the leaving groups and the nucleophile. The concentration will control your speed. But SN1, because it's a unit, because you only have only one, that is the compound with the leaving groups. Okay, so whenever you have R, they don't have a transition state because they will do carbocation formation first. Meaning your leaving group will leave first. Okay, and this one will leave first, and then they'll become what? Positively charged. leaving groups usually what? Electronegative, as you know. You see the trend in the leaving group trend. They're all electronegative elements. So when they grab those the electron here, so they become negatively charged. So when they leave, they still become positively charged. Okay. So they form the carbocation somewhere in your compounds. Okay. So when they form the carbocation, almost immediately your nucleophile coming into the carbocation right away. So this is why in SN1, doesn't really matter because it depends on how fast this compound will form the carbocation is the only matter that determines the whole process. Because this reaction will happen so fast, we're not even count it. Okay? So this is why we call this SF1. Because it only is solely made on the compounds, the leaving groups. So here's one thing I want you to remember. So this will not show you transition state, okay? Transition state. So they will have a leaving group to leave first. So there's two open space, okay? So unlike the one of the SN2, the nucleophile can onto here or on the back. They have a choice now. Okay, they have a choice now because they don't have a leaving group anymore in here, right? SN2, you had a transition state, so this coming onto the back. Leaving group is still there. That's why they couldn't come to the here because they still have a leaving group here. But SN1, leaving group can come here and here because there's no leaving group anymore. It's already left. They're gonna bond to carbocation almost right away. But there'll be two choice. So that means you're gonna have two products. So the one that added on here, where you had a leaving groups, on the back side where you had a leaving groups, half and half. So there'll be two products. Because there will be stereochemistry wise different. Does it make sense? Okay. So let me show you one example. It's always better when you show the example. Okay. Oh, this okay. I'll give you an example soon, but I just want you to remember. Okay. Okay, this is one example here, and then when you look at the reactivity trends. So when you have a bromo leaving group here, and you had a water as your nucleophile, and then they try to measure the reactivity, the speed of the reaction here. This is totally opposite to the ones of SN2. So like I said, SN2 always coming from the back, right? So if it's less bulky, like only 3 small hydrogen, it's easier for them to approach from the back. So it'll be the fastest one in SN2. SN1 is opposite. If it's more bulkier on here, it's faster in SN1. Because can you guess why? Because so you now thinking about this will be gone. So there's no spacing problem anyway. But the most problem is you have a carbocation in the carbon. But if it's more substituted in carbon, this carbocation will be more stable, right? So that is the reason why in SN1 you have a more substitute, more degree of the carbon cation on these groups will be faster in actual SN1 reaction, which is totally opposite on SN2 reactivity trends. So because this one has no spacing problem. The only thing matters is the carbocation stability now. Okay? Does it make sense? Because when it leaves, they're on the plane, the trigonal plane. So they have a space here and here, no space problem here. So only thing that matters is the stability of the carbocation. So this is why SN2 reaction is a bit more opposite to the trend of the activity on your carbons. Okay? Kind of makes sense, right? Okay. All right, that's good. I'm going to tell you a little bit more today, but this is a general idea. More substitute, meaning it's better for the SN1, but it's worse for the SN2. Okay? All right, so the example here is you have this compounds. Okay? And you're gonna treat with the water again. So this is our nucleophile. Okay, you see the solvent is here what? Ethanol, right? So you can now say, oh, this has to be SN1 for sure, by just looking at this one. Okay, I'll tell you more later what about that. Okay, anyway, so if you do this one, you're gonna have a two products. I don't need to do. Okay, and then you have this one here, right? Oh boy. And then you're gonna have the same thing. This one, okay? So there'll be two. So 50, 50, okay? So this is, so now you have we do have two products. You have four different groups here. Okay, four different groups over here. Okay, so here's the thing. This is one. Do you guys remember how to do the Cunningham convention? Do you guys remember this RS configuration? Cunningham configuration. Okay, so this is number 1, 2, 3, and 4. Okay. But this number 4 is on front, right? So we're going this way, which is S. But okay, 1, 2, 3 is going this way, so which is S. But your number 4 is on the front, so switch to the R. Okay, yeah. So then this will be still R, but you have an S over here. So you have two products with a different stereochemistry. Okay, this is kind of a reason why the SN2, SN1, SN2 distinguish is very important. So here's the one thing. I told you, theoretically speaking, 50 and 50, okay? But this will be actually, realistic data is this is 60, this is 40%. Yeah. Can you guys guess why? So when it leave, okay, when it leave, they form the carbocation here. So it'll be on here and here 50-50, right? But realistically, it actually, the inversion is 60%. So you have a other configuration, which is R to the S. But you can also have the same retention of the chemistry, stereochemistry, but it's slightly lower than 50, slightly higher than 50. Can you guys guess why? Remember, so when they formed the carbocation, I said what? The formation, the nucleophilic attack is almost immediately happen, right? So think about it. When the chlorine will leave, okay? Finally they leave. So they have a certain time, and they are leaving, right? But this the nucleophile water coming into the here and here. But I said this is happening so fast, and as soon as it leaves, it attack on here. So there are slightly interacting, very slightly, because will be just about to leave and they bond there. So they have a no spacing problem, but they kind of hinder on this side, on the retention of the stereochemistry. So it's very slightly preferred on the inversion still, even in SN1, because it happens. So when they are just left and they're coming onto the here, so there is just really tiny bit of spacing interaction problem. That is the reason. But the key point here is you're still going to have two different stereochemistry compounds as products. Okay. Obviously, yeah, it won't be on the exam, but I just wanted to. That makes sense, right? Yeah.
Will the two products always be opposite configurations?
Yes, often. So either it will be inversion or retentions. Yes. Because as I told you before, when they form the carbocation, they're all the same plane. So there's only two sides they can approach to. Very good question. Okay, so can I move on? Good. Okay, so I told you the general trend of the reactivity of the carbocation. This will be a bit more specific trends. I'm not gonna lie, this won't be on the exam though. But let me just briefly explain, and then just move on, okay, at least, because those ones actually going to cover in over 2 more specifically. That's why actually I can do. So this is a metric carbocation. This is the primary. This is a secondary. This is tertiary. Because you have 3 arguments here on this carbocation, 2 are on this carbocation, 1, and this is nothing expected. This is a carbon right next to the carbons in the double bond. So we call this a lytic position. And the lytic position is kind of unique because you have a carbocation here, and also you can have over here by just switching the nuclear, the electron pair. So lytic position carbon, those 3 are more stable than the other. So even though it has only 1 R, this carbon here, this could be almost the same reactivity with the secondary carbocation. Same thing for benzylic position here. This is a benzene ring. This is a conjugate ring, which means your double bond and single bond is alternating on the cyclic form. So you have carbons right next to the benzene ring, aromatic ring here, which is the positive charge. This benzylic position can also switch the carbon positive charge here to here to here to. Let me see. Oh, sorry, I drew it wrong. Here, here. So we're moving here, moving here, moving here, here, and moving here. So you can also have some carbocation resonance on here, like it did in a lytic position too. So this is also, quite stable as a secondary carbocation, but obviously more stable form is tertiary carbocation, as I mentioned before. But these 2 will be more heavily discussed in Organ 2. Are you guys taking Organ 2? Okay. So I'll just move on. You won't be on the final exam, but I just want to briefly introduce before you taking Organ 2. All right, so the reactivity trend, leaving group trend of the SN1 is very similar. So this looks like this. It's very similar to this is SN1 leaving groups trend. It's just slight trend change on the leaving groups with here, a little bit here, but it's almost same. So I'll just move on. But I want you to remember this one more. This is the solvent. Finally, so SN1 solvent. So reactivity trend, pure ethanol, 40% water, 60% ethanol, okay. 80%, 20%, and pure water. Okay. So this is a trend. So the more pure water than the ethanol is better for the SN2. I mean, generally speaking, it could be different compounds. But the point here, once again, if you see the solvent as like ethanol or ethanol water mixture, or just water-based, you can always think that it is going to be SN1. It's not. It's unlikely to be SN2. Okay? can also look at it as the compound leaving group is more bulkier or less bulkier. You can also take that, but okay. And then the reason why, so those are the one we call polar protein. Okay? Obviously, ethanol and the water has a, the hydrogen group, like the hydrogen formation, possible compound, so solvent. This is because of that they have some slightly negative charge, polarity on this water here, will actually stabilize your carbocation. So this is kind of a reason why we can have a more stable carbocation compounds in the polar protein solvent here. So we're actually stabilizing the one without the leaving groups, which is better for the SN1 reaction. So if you see those solvent based in their reaction, you can assume they'll be most likely SN1. Okay. All right. So what time is it? Okay. All right. So I'll just cover a few more things, and then we're almost done with the chapter 11. Did it make sense so far? Was it okay? Oh, that's too great. So let's talk about the elimination. So we talked about the substitution now. Let's talk about the elimination. And we're going to talk about the Dice rule over here. So it's actually a pretty simple rule. If you have some bromo compounds, and you can treat it with some sodium hydroxide. Okay, I'm gonna just draw the carbon. Okay. And then some ethanol base. Okay. So if you do this one over here, you're going to have two products. Okay. And then the percentage was this is 81%. This was 90%. Okay. So the elimination is simply happening by the base will pick up the hydrogen. So if this is obviously your base part of your compound, sodium hydroxide. So because this oxygen is the negative charge with the two carbons on it. Okay, and then what it does is when they try to grab the hydrogen here. Okay, so when they base grab the hydrogen. Okay. And then this goes to form the double bond instead, okay? Not replacing the leaving groups. And that push makes to this one to leave. So it becomes alkene. So it's actually eliminating the leaving groups and hydrogen because the base will pick up the hydrogen so they can make the move on to the other carbons to form the double bond. And that leaving group, that electron push, will make that bromo to leave. Okay? So it's not substituting, but it's actually going to make the alkene compound. Does it make sense? Okay. But the thing is, now you have a major product and a minor product over here. Can you actually guess why? This is just coming from what we already learned before. Look at the way there's the double bond. It's in the terminal position, it's the internal position. So what might be the difference on these two carbons? So this carbon with the 2R with 2 hydrogen. Okay? So it's a disubstitute. Those two carbons, this double bond is disubstitute because 2 R's on 2 hydrogen. Okay? You see that, right? And this one is what? There's 1 R here. There's 3 hydrogen on it. Because it formed on the terminal position. Last 2 carbons over here. So it's only what? Monosubstitute. So which one is more stable? This one, right? Okay. Because it's more substitute. So that is why they prefer to form this products over this one. Okay. So that means they sometimes pick up the hydrogen here, I showed you, but they can pick up the hydrogen on the terminal position too. That's possible. Base comes in, grab, goes there, goes there. So then double bond on the terminal position. But it will be less likely than the previous one because it's much more stable. So we call this dicey rule, meaning you're gonna have a more substitute alkene than the other as a major products whenever you do elimination. Okay. Does it make sense? Okay. Let's do one more. Okay. I would like to try this one real quick. Maybe. Okay, I'll show you the same, but just different. Okay, can you guys try this one real quick? And then that will be all today. I'll finish up the chapter 11 on Friday. It will be really quick. We're almost done. Because the elimination is the only very briefly covered in chapter 11. Then we'll start the review on Friday. Hopefully, I think we can do Friday and Monday as well. Okay, so this one will be what? This one, right? Okay. Or this one, but it will be terminal anyway. Okay. So, which one do you think would be major, or which one would be minor? It would be 1 or 2. Okay. So which one is major? 1 or 2? 1, perfect. Yes. Because see this one, there's 1, 2, 3, right? And there's only one hydrogen, right? So it's what? Tri-substitute. Okay. But this is what? 1, 2. So it's di-substitute. So this will become major over this one because it's a more stable. Makes sense, right? Does it make sense? Oh, good. So yeah, I'll finish it today. Let's do extra.